This is Ted Doskaris. Today is February 26th, 2022. It's about 4:35 p.m. I'm making a video here of a test of the Aristo-Craft RDC1 where I'm going to check the voltage going to the lights, this is the chassis of the RDC1. It's on Bachmann rollers to pick up power from the track. And so I'm going to test what happens, and there's a surging effect as I increase the voltage on the track up from 0 to about 4.5 volts or so. There starts to be a surging effect. It could be a little higher voltage than that. I'll demonstrate. So I'm using an Aristo-Craft earlier train engineer here, and there's the receiver. There's the power supply of the famous battery charger power supply it's referred to. And I have an oscilloscope, Tektronix 2465 350 megahertz scope set up here, where I have two of the probes in A-B mode, differential. I have a third probe going to the track, right across the track here, and that's this probe here. And I also have just a DC digital voltmeter there. And the train engineer is set in linear over here. And so I'm going to gradually increase the voltage on the train engineer. And let me see if I can get a probe here to point with. Right now the voltage isn't being applied. So channel 1 and 2 are differential A-B, and that's the center trace. So this would represent a ground here in the center trace. And the third, channel 3, is set up for the ground down here. And it's 5 volts per centimeter on the gradient here. And so I will then start to increase the voltage here. And we'll see it over here on the track here. That's more than I wanted to increase it. So it's about 3.5 volts roughly here, and you can see on the scope, which is this bottom trace here, it's 5 volts per centimeter, corresponds to about 3.5 volts here. Camera's not going to focus too well, I don't think, and this maybe it's too bright. So far the wheels aren't turning and the lights are not on. And you can see the lights. There's, on this long slender board, there's 1, 2, 3 incandescent lights. And then on the main circuit board, there's 1 and 2 incandescent lights. So Aristo-Craft refers to this board with the switches on it and so on, and all the electronics as the main board, and this is called the subboard, the long slender board. So I'm going to increase the voltage now slightly. The trucks are turning, and let me back it down a little bit. So about somewhere near 5 volts. The wheels are turning. You can see kind of how the wheels are turning here. There's a little tick mark with a pin on the rollers and the Bachmann rollers. The lights aren't lit yet. And also the center trace doesn't show any voltage across the lights, and that's where the scope is connected across one of the lights. They're all in parallel, all the lights. And this device here on this right angle board is what's called a PIC processor, and apparently Aristo-Craft calls it a DC-DC converter here. And apparently it's a form of pulse width modulation when it's intended to work. So right now there's not enough voltage to activate it, it seems. And so the wheels are turning smoothly. So I'm increasing it to about 5.8 volts. And on the scope that corresponds to almost 6 volts here on the bottom trace. The middle trace still isn't doing anything, so the lights aren't being energized by this PIC processor DC-DC converter board. So if I increase it a little bit more, that's 6.4 volts roughly. And interestingly, we can see now there is some pulsing going on here from 0 to 2 volts across the lights. Let's see if I can synchronize it a little bit better. It seems to be varying, and it's not syncing too well because it's varying both in pulse width and pulse period. So, but it doesn't seem to be surging as such, as far as the motion of the motors in the trucks go. Now, if I increase it a little bit more, I can see the lights, just the intensity is just beginning to come on just a little bit and then turning off. The filaments. They're just beginning to illuminate here, say for this filament here, and then it's going off, and the others are doing similar. And notice how the voltage seems to be changing at 6.65 roughly, dropping to maybe 6.3, as low as 6.3. 6.4, 6.45. And you can see here, now this is the voltage that's supplied across the tracks. And so you can see it varying somewhat, as though the load is, as though the power source, which is the Aristo-Craft train engineer, is being drugged down slightly while it's doing that. And so the wheels, the trucks, the motors are surging somewhat when that happens, because the light goes on and goes off. Now if I continue just the next notch above that, it's much more prominent. You can see the lights, hopefully it shows up in the camera. They come on with some brightness and then turn off periodically. The motors are surging in concert with that. Now the voltage across the track is varying from 7 and maybe 7 1/4, 7.3, 7.4, and dropping down to 6.6, 6.8, somewhere around there. And we can see the effect on the oscilloscope here. See if I can get it so you can see it. So it's going from, this is applied across the tracks now. It's going from 0 to again about, well, in this case, 1, 2, 3, maybe 3.5 volts, or 2.5 volts, because or 3 volts, because each centimeter is 5 volts DC. But you can see the pulse is changing both in frequency and pulse width in the period here. Here's where these two dotted lines are. It happens to be 227.5 microsecond period. But you can see the well, here's the here if I move this to here. So apparently about every 150 microseconds roughly is the period where it's changing, 148 or so. Now as I increase it more, and you can kind of even hear it surging. I go up. So if I increase it more, now there's less surging, and the track voltage is varying between, not too bad now, between 9 and 7 volts. And the lights are on a constant illumination. And right now there's a DC across the lights, and again the bottom here you can see it's about 7 volts. That's the waveform across the track, which is a solid DC line. And over here, and then this is the voltage now. It's a steady state DC without any pulses. It's about 1, 2, 3, almost 4 volts across, maybe 3 3/4 across the lights. Now if I increase it some more, everything is operating smoothly and the motors are going faster. Alright, so there's about 10 volts across the track. That corresponds to here, 5, this is 0, 5 to 10. That's the waveform across the track. And this is the waveform, again, it's DC, it's not pulsing now. So that's about 5.5 volts DC right across the lamps. So if I keep increasing, now you can see here, there is a point. Let me back it down. There we go. See if I can synchronize it better. I had this first one off a little bit. All right. So it's triggering on the leading edge, and right now it's 163.5 microseconds between the repetition rate of the pulses. I don't know if it's showing up here on the camcorder. And the pulse width this day is it's changing there. Let me back it down again. So here you can see all the lights they're brightly illuminated. 12 volts across the rail roughly. Again, that corresponds to the bottom trace, where it's a solid steady state DC, about 12 volts. And you can see this pulsing that's applied across the incandescent lamps here. And it's going from 0 to about 7 volts. Alright, and at a period of 163.5 microseconds here. Again, it may not show up too well here on this video. So, if I measure the pulse width, it's about, it says 129 microseconds. Alright, and here's the period, about 165 or so microseconds. So if I increase it further, now the pulse width is changing. Let me back it down a touch. Seems to be a threshold right there. So the period hasn't changed here. It's at 165 microseconds. Voltage across the track is now 13.1 or 13.15 or so. And of course motors are running faster in the trucks. The lights are illuminated. Now if I increase it more, again it reaches a point where, as though it thresholds. Now again, the lights are still bright, but I guess not as bright as they could be if it just had a fixed DC level. But it's going now from, this is across the lights, it's going now from 0 to 10 volts. Period hasn't changed at 165 microseconds. The pulse width now is about 72 microseconds. So if I increase it again, you can see the pulse width went down a little bit. I'm at, say, 16.5 volts across the track. Motors are running really fast. And the pulse width became somewhere near 63 microseconds. About 63 microseconds. It's the time shown here. Probably can't see it. And if I increase, and the peak level went up to about 12 volts here. It's 510, about 12 volts. All right. Now if I increase it more, now I've got about 18.3 across the track. That's the maximum this particular train engineer will deliver. And the lights are relatively bright. The motors are going as fast they're going to go is coming out of this train engineer. And the pulse width now measures 48 microseconds. Okay, so the period about 165 still. And again, the lower trace, which represents the waveform, which is a solid DC line across the tracks, is 1, 5, 10, 15, 18 volts. So that corresponds to the DC meter, roughly. So if I reduce the speed now, reduce the voltage across the tracks, you can see the pulse width changed. The period did not change yet. Period did not change. Period did not change. It's slowing down. So now it became what looks like a DC level. Now, it's just okay, now this is the strange phenomena when it reaches a certain point. And now it goes into another PWM phase. But it looks as though the period is also changing, varying and coming back to 165, as well as the pulse changing, the pulse width changing. So if I move this period here to where it's the maximum, it's about 211 microseconds. So the period is changing from 211 back to about 165 microseconds. And the pulse, of course, increases. At a varying rate. A very strange phenomena. And this is when it's surging. The motors are surging. So apparently what must be happening is that when the motors are started to drawing a lot of current, it's or relatively more current, this circuit here with the PIC processor apparently doesn't receive enough voltage across it to function, and as the motors then change speed, then the circuit comes into play and the lights start to begin to illuminate. So apparently it's affecting, you can see the track voltage here it's being affected. So if the source supply, which in this case is the train engineer, were say a car battery or something like that, or something that had a very low source resistance, then I wouldn't expect this to happen. So now I've added a polyfuse here, and I've checked the voltage across the polyfuse, and the polyfuse is not tripping and not changing any value. So I've verified that, because if that were starting to trip, and you wouldn't think it would at such low voltages here, that could create a phenomenon like this. So at any rate, the next thing to do is I'm going to see if it's drawing a current spike based on the activation and deactivation of this at this particular voltage applied across the track. Now, to measure the current, I put the probes across. This is a 1 ohm resistor that's in series with the wires that go to the tracks. And normally I have it shorted out with a clip lead here. And so Ohm's law, E is equal to IR, so voltage is equal to current times resistance. So if it's 1 ohm, if there's 1 amp going through that resistor, there'd be 1 volt across it. So at any rate, I set up the scope to try to trigger on that, and I reset the volts per division on the differential here. Again, the scope probes in differential mode are across the 1 ohm resistor, and I tried to trigger and find if I could find any spikes that are occurring at the surging rate, and I really can't see any. And I've changed the volts per division to as much as down to 50 millivolts per division to try to see something. But I would have expected a fairly large spike, and I'm not seeing it. So let me put it back up to at 5 volts per division. There. And change the seat to auto. Alright, so, but I can see the track voltage is still varying, so maybe it's between the train engineer up here and all the wiring and the track and so on. Maybe it's the inductive reactance of that's going on. So at any rate, and maybe also the resistance between the rollers and the track through this mechanism here. Maybe that's coming into play. So at any rate, it's a very strange phenomenon, and just something to be aware of.